you're watching the Earth go around the sun or whatever it is. So Einstein said that means there's no such thing as absolute space, which kind of follows if you think about it. But that's it's a cool but difficult thought process.
Right. I mean, that's essentially what's happening when you're on a plane. And if you're throwing a ball up in the air and catching it on the plane, it's happening at a much smaller scale, right?
Yeah. I mean, you're flying at whatever 600 miles an hour relative to the ground.
But it doesn't seem like it when you're sitting there.
Yeah, and Einstein elevated that to a principle and said, if you're moving if you're not accelerating, you're just moving at constant speed in a plane, or now. I mean, that's essentially what we're doing now. We're moving around the sun at effectively constant speed. Then you can't tell. So there's no experiment you can do. We could look at the decay of a radioactive nucleus or some electricity and magnetism or bounce a ball, have a pendulum, whatever it is. And there's no experiment you can do to tell you whether you're moving or not. Therefore, that concept has no meaning. Because you can't measure it. And that's led Einstein to relativity. Wow. So that's the basis of general relativity, which is our best theory of the universe.
Now, why is it that we think that the known universe is larger than what we can observe?
Well, one point is that it's expanding, and we always see the same radiation out there, so the glow of the Big Bang. But there are some deeper reasons. The one, from the theory of inflation, the best way to explain the universe, the properties that we see, is that it's very much bigger than the piece we can see. So, for example, we measure space to be what's called flat. I don't even have to say what's called flat, it is flat. So if you imagine slices of space, let's imagine slices of them at different times. So you just slice the universe and say there's a big sheet, it's like this table.
Okay, like a table.
There's a sheet of space, and there's another sheet, and another sheet. And it can have a geometry, right? It can be flat like a tabletop, or it could be curved like a sphere, or it could be curved in the opposite direction, sort of like a saddle or a bowl. And we can measure that. And when we measure it, we see it's absolutely flat. And that's a very unusual thing for it to be like. It requires, because what Einstein's theory says is that the shape of space, that the curvature of space is determined by the stuff that's in it. That's basically Einstein's theory of general relativity. Put stuff in space and it curves it and bends it and warps it and stretches it and so on. And what we find is that there's precisely the right amount of stuff in the universe to have a completely flat universe. And the explanation, the most favoured explanation for that, is the universe is way bigger than the piece we can see. And so it's like looking at a piece of the Earth. If you look at a little 1 mile square of the Earth, right, then it's flat. Right? You have to look at big distances, kind of of order the radius of the Earth, or not, bigger than 1 kilometre anyway, or 1 mile, to see that actually you're on a curved surface. And that's one of the ideas about the universe and why it appears to be the way that it is, because it's way, way bigger. So we're just looking at a little piece, and that's why it looks flat. And that's one of the ideas.
Now, when you say flat, like that, my brain doesn't understand this. Because from our perspective, when you look up at the Milky Way, you see all these stars all over the place. So if you're saying flat, like how much height and what are you saying? So in terms of like the way to measure it.
The best way to think about it is not to think of 3 dimensions of space, because then we can't picture it.
Okay.
But you can think of 2, like this tabletop, and that's all right. We just forget the other one for now. And so you know what flat is on this table. I mean, you could define it. So you could say, for example, that if I draw a triangle on the top of the table, then all the angles add up to 180 degrees. So that actually defines flat. If you did that on the surface of the Earth with a big triangle, then the angles wouldn't add up to 180 degrees. Or you could draw a circle and say, what's pi? So pi is the ratio of the circumference of a circle to its diameter. That's only true on a flat surface. It's different if the surface is curved. So you can define flatness.
So when you're saying flatness, what is the height and what is the width? Like if you're talking about it as if it's a table, there must be some sort of there's a dimension to it, correct?
Oh yeah, there's a third dimension of space,
right.
But the same applies. It's just a generalization of geometry. Then, so you can the point is we can picture it in 2 dimensions, but you can draw. You can quite literally, you can imagine sending light beams out, and we do this measurement actually. We can look at the most distant light we can see, which is something called the cosmic microwave background radiation, which is, if you imagine looking out, if you look at the Andromeda galaxy, which we can see with the naked eye here in LA, you can see that. It's the most distant object you can see with the naked eye, and it's about 2 million light years away or so, which means the light took 2 million years to get to us. So it's a long way away, but it's very big. So as you look further out into the universe to more and more distant galaxies, you're looking further back in time, because you look at something that's 1 billion light years away, then the light took 1 billion years to get to us. So you see it as it was 1 billion years in the past. And we can actually look so far out that we can see almost back to 13.8 billion years ago, which is very close to the Big Bang. So we can look to light that began its journey before there were galaxies. And that's the oldest light in the universe, which is, by the way, one of the pieces of evidence when people say I don't believe in the Big Bang. The answer is, well, you can see it. So you can actually, it's just there. You can see it. We have pictures of it. That light, it turns out that there are sort of structures or ripples in that light, which we can use as a ruler. So quite literally, as a ruler on the sky. And then, because that light's been travelling through the universe, we can see how that ruler's been distorted as the light has travelled through space. And so we can infer whether space is flat or curved, or how it's warped, if you like, just from that measurement. So it's a beautiful measurement.
Is it possible that in the future we'll be able to see past 13.8 billion years?
Not with light.
Not with
because
light.
What the picture is that before, it was released 380,000 years after the Big Bang. A very precise number. You might say, how do you know that? Well, before that time, the universe was so hot that atoms couldn't form. So you had a soup of electrically charged particles that were just too hot for electrons to go into orbit around nuclei. So the universe was opaque to light. So you just couldn't. It's like almost like a big glowing star. And then when it was expanding, it cooled past the point where the atoms could form. And at that point, it becomes transparent, really almost instantly in a cosmic timescale. And so the light could then travel in straight lines through the universe, and we can see that light. So we see the light from that time, but further back than that, it's opaque, so you can't see past that with light. But you can potentially with gravitational waves, which is this measurement that got the Nobel Prize a couple of years ago, the LIGO experiment here in the United States. And that, it looks for ripples in the fabric of space and time. And in principle, if we had a big enough detector, you could see the ripples from the Big Bang. So you could take an image of the Big Bang in gravitational waves, which would be. But you need an enormous sort of space-based detector that we can build anytime soon.
You know, obviously this is all through equipment and technology that's been invented over the last few hundred years and perfected. Is it possible that things could get better and you could get some ability to detect things even in a far more distant way?
Yeah, I mean gravitational waves are incredible. I mean, Einstein predicted them in 1915. Never thought they'd be detected because you need such a you need lasers, but it didn't have lasers. But they think LIGO, this experiment, was half up near Seattle in Washington State and half in Louisiana. So they've got 2 detectors. And they're basically sort of, 3-mile long laser beams that just sit and measure the sort of stretching and squashing of space as the ripples in the fabric of the universe go through. And what they've been observing, collisions of black holes. So you can imagine how extreme, colliding black holes. It's an incredibly extreme event. So it shakes the fabric of the universe, and the ripples come across the universe. And these laser beams, which are just basically rulers, can detect it. They just sort of ring almost like, just vibrate as the ripples go through in space and time. Kip Thorne got the Nobel Prize last year for this. He was one of the greatest living physicists. So I once saw him describe it as a storm in time. So you've got this time storm. It's a beautiful image. So that technology is incredible because the change in length, I can't remember the exact number, but it's way, way, way less than the diameter of an atomic nucleus. So the change in length of the beams, it's a tiny measurement, but we can do it.
So the collision of black holes, the idea that you can detect that.
Yeah. The paper, the first paper they published, They're two black holes, and they were about 30 times the mass of the sun each, and they were orbiting each other and spiraling in towards each other, and they accelerated. At one point, they were approaching each other at 1/3 the speed of light, and they accelerated to 2/3 the speed of light in 1/10 of a second, and then hit each other. And the explosion, the energy release, was, I think I'm right, it was something like 50 times the energy release that the power of all the stars in the observable universe glowing. And it was something like 50 times that amount of energy for a tiny fraction of a second. But it's an unimaginably violent event, and that's why our detectors can see the ripples that makes in space and time. And we detected, I can't remember, it's 2 or 3 of them now, and also 2 neutron stars colliding. We saw that as well with it. So it's an incredible machine, which is why it got the Nobel Prize.
Now, there's a supermassive black hole at the center of every galaxy.
Yeah.
But there's also other black holes that aren't necessarily in the center of galaxies.
Yeah, so these little ones, the little, they're a few times the mass of the sun, and they're from collapsed stars. So they are stars at the end of their life, very bigger than the sun, more massive than the sun. But they run out of their fuel, and they start to collapse because gravity squashes them. And if they're sufficiently massive, then there's nothing that can stop the collapse. And so they collapse, as far as we know, to a point, essentially an infinitely dense point. We don't really know what happens we don't know what happens right in the middle. But they collapse to such an extent that there's a region around it from which light can't escape. And so nothing can escape. And that's a black hole.
And what happens to them? Do they travel? Are they moving through space?
Yeah, they're still stars. They're still there. They're surrounded this region where if you fall in, it's called the event horizon. And if you go across that horizon, then you are going to the centre. There's one way of thinking about it, which is quite cool, which is that the time and space sort of flip with what it's think about it. So in the same way that we are going into the future now, so we're going to tomorrow. There's nothing we can do about it. In the same way, if you fall in across the event horizon of a black hole, you are going to the middle, the singularity it's called. So that's your future. Every line of your future points to the centre of the black hole. So it's kind of the ultimate of no escape, the ultimate prison. You're going to get squashed to an infinitely dense point.
Not every star becomes a black hole at the end of its life?
No, because if something like the sun,
we have a small star.
It's quite small, yeah. And when it collapses, there's a sort of a pressure, force, if you like, which is caused by the fact that electrons don't like to be very close to each other. So it's called the Pauli exclusion principle. But essentially what happens is that, so as they get squashed closer and closer together, they move faster and faster to sort of get out of each other's way, if you like. And that makes a force which holds them up. And so that creates what's called a white dwarf star. So you can have a blob of matter. They're about the size of the Earth, but they're about the mass of the sun. And so that's for smaller stars. They end up as these white dwarf things, which are very dense objects. There's another version, which is called a neutron star, which is the same thing, but for neutrons. And they move faster and faster. So if it's massive enough that it overwhelms the electron thing, then the electrons sort of crush into protons and turn into neutrons, and the whole thing starts again. And so a neutron star can be, at least 1.5 times the mass of the sun, let's say, but it can be about 10 miles across. So that's an incredibly dense ball of matter held up by the neutrons moving around. It's got a fancy name. It's called neutron degeneracy pressure. But that's what it is. But if you go even bigger, then even that can't hold it up. There's no known force that we know of to hold the thing up.